Okay, let's consider Earnshaw's theorem. It says a charged particle cannot be held in a stable equilibrium by electrostatic forces alone. So let's consider this example. Here you have charges Q in the corners of a cube. And suppose we want to look at the point in the center here. So by symmetry, you realize that the electric field must be zero, and thus also the force. So you have electric field from that, but then you have electric field from that, so they cancel. So pairwise cancellation here in the center. So that's what I'm saying here. Electric field equal zero. Right. And in electrostatics, we have learned that there is a relation between electric field and electric potential. And it is the negative gradient of the electric potential. But at this point, the electric field is zero. So the gradient is zero of the potential. So that means in this problem, X, Y, Z, it's a multidimensional problem. And to find a critical point, all we need is the gradient to be zero. You can simply realize that of course, for a point to have any chance to be a critical point, the force must be zero. Thus, the electric field is zero. It's like in one-dimensional analysis. You know, if you have a function of x, take the derivative, set it to zero, that is a critical point. Then the question is it a max, min, or maybe a saddle point? And similarly, in multidimensional analysis, it's again, check that the gradient is zero, and then we need to determine what kind of character this point has. And unfortunately, it's not just taking the derivative again and find out if it's greater or less than zero, because this is a multidimensional problem. So we do it in analysis by looking at the Hessian matrix. It's given by this. Here is the matrix. And here is the derivative d2v with respect to dx2. So the second derivative with respect to x, and the second derivative with respect to y, and here c, and here are cross derivatives, which I don't really care about right now. And the theorem in multidimensional analysis says that if all the eigenvalues of this Hessian matrix are greater than zero, then we have a minimum, a stable point where a charge could be situated and forever be stable. And likewise, if the eigenvalues are less than zero, then you have a maximum. And of course, a charge placed at the maximum would not be stable. I mean, it would be just falling off. And if you have mixed signs of the eigenvalues, then it's an unstable saddle point. And then, so a charge placed there will not remain there forever. A small perturbation in the moment of the charges at the corners would make that a charge over here, it will fall off just. So just because f equals zero, it doesn't mean that it will be able to stay there. And that is exactly what this theorem is saying here, Earnshaws Theorem, that it can't be held stable by electric forces alone. And the final proof of this, since you have studied linear algebra, hopefully they taught you that the trace of the matrix H, that is the sum of the diagonal elements, this plus this plus this, okay? And it happens to be the sum of the eigenvalues of the whole matrix. And those are free also, of course, right? But we know from Laplace equation that the nabla squared v, that is actually exactly this, vxx plus vyy plus vcc. And inside here, if we look inside at the point in the middle here, there are no charges inside a volume, a sphere, for example, inside here. So Laplace equation equals 0. So what does it mean here? So it means that the sum of the eigenvalues is 0. And then, of course, if all eigenvalues were positive, for example, well, then it would not be 0, would it? It would be greater than 0. Or if all eigenvalues were negative, yeah, then the sum would be negative. But this proves that it's 0, so it must be mixed eigenvalues here, negative and positive. So, or all equal 0. So what it means, if you have mixed signs, I mean, for stable, where we really know how the saddle point, I mean the critical point is, you need all signs to be the same to really know it's min or max. But mixed signs, that means it's an unstable saddle point. So we just proved this theorem here, that the charge here will not stay in this situation. Earnshaw's theorem. All right, thank you very much. See you later.